Last time we did some advanced statistical calculations with Excel to calculate the uncertainties in our gradient, and then we enhanced the appearance of our graph as a result. Now, this one, we're going to use the gradient and its uncertainty to calculate the Coulomb constant from our experimental data. Let's go back to our theory page for a moment. So we have our theory page. Now, we had said earlier that the gradient A of our graph should equal the constant K by Q by Q. And then rearranging that, we have a formula here to calculate the Coulomb constant, the gradient divided by the product of the charges Q and Q. Now we have all that information available. Remember, all the way back at the very start, we had noted the size of the two charges in this experiment. They were controlled, but they were still there as numerical measurements. And we have a gradient over here. So we are going to, in fact, what I might do, so I don't forget that, I'll do the screen snip trick once more, where I just capture all of that and drop it over onto the page I'm working on. Oops, that was a little big, wasn't it? There we are. Now, I'm going to try and use this formula for the value of the Coulomb constant. Again, start with an equals. I need the gradient. That's the value stored there. It needs to be divided by a product of two numbers, little q, which is that one. Now that number is 3.5, but don't forget it is microcoulombs. So I will come down here and write multiplied by 1 exponent negative 6. That's the Excel code for 1 by 10 to the power negative 6. Then that's literally 3.5 by 1 by 10 to the power negative 6. And then I will put the 5.5 and again with the 1e negative 6, close off the bracket. And that gives me the value of the Coulomb constant. That's in excellent agreement with what we would have expected. I might just increase the decimals on display there a little bit. See, it's not perfect. In a textbook value, you'd get 8.99, but we're very close. Now, let's take a look at the uncertainty calculation here. When we multiply or divide quantities in order to get an answer, we add the relative errors in those amounts. So the relative error in K will be the relative error in A added to the relative error in little q added to the relative error in big Q. That's that calculation there. And we have all of that information available. We have the uncertainty value, the delta A. That's that number. We have the deltas for the little q and the big Q. They were noted originally. So that's the uncertainty, delta of little q and delta of big Q. So in this cell here, just ignore my OneDrive errors. In this cell here, I'm going to be implementing this formula. So here I go. Now, I think I'll use brackets to be extra careful. Uncertainty in A divided by A, added to the uncertainty in little q divided by the size of little q, added to the uncertainty in big Q divided by big Q. You can see the formula appearing here in the formula bar, and you can also see it down here before I press the enter key. Now, I had pre-formatted this one to be percentage. If it happened to be in numbers, it would have come up as a decimal. This is the relative error in K. Formatting it as percentage is probably a good idea, and 2 significant figures in a percentage error is acceptable. I wouldn't be going to more than 2. That's getting a bit extreme. 2 significant figures is fairly good for a relative error. Now, what I'd also like to know is the absolute uncertainty in my answer for K. So this gives me, basically I just multiply through by the value of K into all of this. There it is there. Everything in brackets is already calculated. The value of K is here. So I should be able to just go the value of K multiplied by, it's not letting me. Oh, don't be annoying, Excel. Let's try it this way. Let's try that one first, multiplied by the value of k. That's better. Now that gives me, in scientific notation, the uncertainty. Notice this one is by 10 to the power of 9, and this one is by 10 to the power of 8. It's an order of magnitude less. Usually with absolute errors, we round them to one significant figure. So I'll round that to 5 by 10 to the power of 8. And that would really be in the decimal place here. If you like, that's 0.5 by 10 to the power 9. That tells me I should round this to 9.0, where the uncertainty is in the same place value as the rounded digit. So that's my answer, plus or minus 5 by 10 to the power 8, which is a relative error of 5.6%. And that's the last thing we needed to do. So we have done a full analysis of this experiment, and we have used the data to calculate the Coulomb constant with an uncertainty of 5.6%. Thanks for watching.